Hi, welcome to the QNX Virtual Campus lecture series. In today's video, we're going to be talking to Colin about the instrumented kernel. These days, CPUs are getting increasingly complex, and it can be really hard to figure out what's actually going on inside your system. So, the instrumented kernel leaves behind a trail of breadcrumbs for our system tools to follow, and it adds a lot of insight as to what's really going on. Colin's going to talk a lot more about that. Here he is.
Hi, I'm Colin, and I'm going to be talking about the instrumented kernel. So what is the instrumented kernel? Well, the instrumented kernel is a variant of our standard QNX microkernel that has instrumentation hooks put all over the place to fish out all sorts of information to help you understand your system better. In this day and age, embedded software is so complex and has so many people working on it that it's really hard for everyone to understand what the system is doing at a global level. And this kernel information that we can provide allows you to see that in extremely high levels of detail. Okay, so what information do we get out? Well, pretty much everything, but to go through it, we have instrumented the process creation and destruction points, so you'll see processes coming and going. You get to see their name, their parent, their children, you see them spawning and forking. You get the threads coming and going, you get the creation and destruction, and you also get the scheduling state changes of the thread, them becoming ready, running, getting blocked on a mutex, getting preempted by a higher priority thread. You get the priority information of those threads, and of course, as integrated with our partition scheduler, you get all of the partition information as well. What else do you get? Those threads, once they're running, they'll actually make kernel calls, and so we log all of the kernel call entries and all of the kernel call exits and the arguments passed into those kernel calls. And in the case of message passing, we also log the first few bytes of the message so that you can actually get an idea based on the type code that's in your message on what that message is. Last but not least, we log hardware interrupt entry and exit events. So you can really see the interrupt activity on your system. You might see a burst of interrupts. You might see a delay between an interrupt going off and the handler running for it. You can also see the user interrupt handlers being called and the user interrupt handler exiting, and whether or not it returns an event or not. So all of this information, and it's a lot of information, gets logged into a ring of buffers. The number of buffers is user configurable, so you can allocate as much memory or as little memory as you want to this ring. I'll get into why you might want to change that later. But it's logged in this ring of buffers. As each ring is filled up, a pseudo interrupt handler is called to notify a user level logging daemon that the buffer is available for logging to disk or whatever offline storage that you may want. One of the features of this is that we can actually leave the ring in what we call ring mode, in which case each buffer is overwritten as needed. So it's kind of like a black box flight recorder. This is great for long-running situations where you may not see the issue that you're actually trying to capture for hours, days, or even weeks, and you just want to capture that precise moment when things went wrong. Okay, so getting on to getting these events out of the system. Well, as I said, we have a pseudo interrupt handler that the user mode daemon can attach to, and as each buffer is filled up, the daemon gets this interrupt call out, and it can then copy the event buffer, which has a direct map to, into persistent storage, or it can blat it across the network to your analysis tool. We have two daemons. We have tracelogger, and tracelogger is a command line tool that you run actually on the target, and it logs either to a file or to shared memory. And that's great if you have a target that doesn't have a network card, or it has a high-speed disk, or it has at least plenty of memory. It is also the most efficient. It does it with the minimal amount of impact to the system. And the other daemon that we have is QCon. QCon is what you run when you're connected. It's also used by the IDE, the Momentex IDE, for connecting and fishing out all sorts of system information. But it also has the ability, as I've mentioned, to act as a tracelogger daemon and to automatically transfer the file from the system to your IDE for analysis in the System Profiler plugin. Okay, so that's the gist of the information that you get out and how we get it out. But what sort of scenarios are you going to use this for? Well, the killer application for this is, as I've said, is understanding your system as a whole. In today's software industry, we can often have multiple teams working on multiple applications that at systems integration time need to be brought together and run on a target. Now, these guys might not ever have talked together. They may have been working off a functional spec. They certainly don't understand how their applications interact together. You can actually use the instrumented kernel as a means of observing the interaction between these discrete applications and detecting all sorts of issues. So you can actually have a team that knows nothing about the actual application logic, and yet they can immediately pinpoint problem areas and bring this to the developers. Once you've pinpointed these areas and you take them to developers, it's surprising how often they're actually saying, wow, I didn't know it was actually doing that. The level of complexity within frameworks means that often a lot of the system activity is hidden at a very low level, and the developer is actually using a highly abstracted API. So this is another area that you can really gain a lot of information about what's going on. Another area that you can use this for is optimizing the CPU usage. One of the areas that we've seen this bring immense benefits is trying to optimize the startup time of a system. Now, in today's consumer devices such as radios, smartphones, GPS navigators, MP3 players, the user really doesn't want to wait forever, 30 seconds or more, for your system to boot up. So you really need to squeeze as much out of that CPU as possible. The instrumentation you get out of the kernel really helps you in this respect, because you can see immediately when there's idle cycles in the system. Now, idle CPU time, when you're trying to optimize the startup time of the system, it's the killer. You want to get rid of all that. So, and it's the sort of thing that this information, it pops out at you immediately. Oh no, our system is idle at that point. Why? And it'll tell you exactly why. It'll say, application Fred is blocked waiting for application Bill to register its path name. Well, while we're waiting, there's plenty of other things that we could be starting. So this sort of information allows you to fill in the blanks, basically. Say, all right, well, let's start pipe while we're doing that. You can get rid of all of that idle CPU time. You can really save a lot of time in your startup very quickly by just a simple reordering in most cases. And the other thing that you can see is the bottlenecks. You can see the resource contention. You can say, aha, everyone's blocked on that mutex. They're all waiting for this file to appear. People are waiting for an interrupt to go off. We can do something else in the meantime. I'd like to stress that the use of the instrumented kernel and analyzing the data from it shouldn't be seen as a last-minute optimization step. You want to be able to understand what your system is doing as early as possible in the project. You can see problems before they arise, and if you need to make architectural changes, you can make them early in the project before they become a roadblock for your project schedule. So in closing, I hope that this has raised your level of interest in using the instrumented kernel, and I hope that it really helps you optimize your system more easily and brings you a lot of benefits. Thanks.